Okay, today I would like to introduce Ian Treviranus, who is going to talk to us about particle characterization of Trona, which is a fairly important mineral for the power industry and for our environment. So Ian, I'd like to turn it over to you.
All right, thanks, Jeff. My name is Ian. We're going to have, probably about a 40-minute formal presentation, and then we're going to follow it up with a Q&A afterwards. I don't have too many slides. You shouldn't expect 35 of the 40 minutes to be about Trona. A lot of it is about, if you're in the industry, you know why it's important. I'll talk about that for only a few slides. Then I'll give some example data, and then what I'm going to do is show you how you can interpret those results correctly and also use the technologies we'll talk about today to help you screen incoming material or monitor anything that's coming off your mill. So before we start, I did look at the registration report for the webinar where we ask you what you'd like to learn from today's presentation, and a lot of the feedback was about kind of related issues with general particle sizing. So maybe not specifically related to Trona, but how do you set good attainable size specifications? How do you understand and interpret your particle size results a little bit better? And then also a few of you wanted to learn more about the technologies that we're going to be featuring in today's webinar. So what I have here up on the screen right now are different resources. These are all different recorded webinars we have up on our website, where each one will go into a lot more detail about these individual topics than I will today. And what we will talk about today is, first, I'm going to go over what is Trona, for those of you who don't know. Why are power plants using Trona? Trona has many different uses, but really where we've seen the most interest from the measurement perspective, the size measurement perspective, are from power plants. The impact of particle size and surface area on Trona performance. We'll talk about the technologies that allow you to measure the size and surface area. And then I'll have several slides about how you interpret the particle size results before finishing off in the Q&A. So what is Trona? If you do a Google image search, you will come up with a very high-tech or high-designed baby chair. It's confusing. You'll find a very beautiful picture of a mineral formation at sunrise. Apparently, Trona is a city where its residents consider it beyond the end of the world. It is a nutritional supplement. It's this guy standing in a desert. And the correct answer, of course, is it's a material that's mined. So what is Trona? It is naturally formed sodium sesquicarbonate. It has this chemical formula, so it's a combination of sodium carbonate and sodium bicarbonate that's been hydrated. And why are power plants using Trona? It's useful not, there's kind of the big-minded reason why Trona is useful, and then there's the government regulatory reason why Trona is useful. So the EPA regulates SO2 and SO3 emissions, which is important because if too much of that material is ejected into the atmosphere, it's been traced to acid rain and certain respiratory issues. So they regulate how much certain plants, certain stacks can emit. And there are multiple strategies to remove these materials, and a common and very attractive option is called dry sorbent injection. That's where you take a material like Trona or perhaps sodium bicarbonate or maybe a more exotic third material, inject it directly into the flue gas where it will react with the SO2 and SO3 and precipitate it out. So then the precipitate is either captured as it's carried along in the flue gas stream. It's either captured by an electrostatic precipitator or by a baghouse. So either way, it's removed with up to 90% efficiency from the flue gas. But why Trona? Trona is nice because the capital cost of injecting the Trona, supplying it and injecting it into the flue stream, is relatively low compared to traditional scrubbers. We've gotten that data point from several users. Its operational cost is directly proportional typically to the sorbent cost. So as the cost of Trona goes up, so does the operational cost and vice versa. And the SO2 and SO3 removal is proportional to the reactivity of the Trona. And if we were to follow that down, what that means is that the reactivity is directly proportional to the surface area, and the surface area is directly proportional to particle size. So this makes a certain amount of sense. And so a lot of times what operators have to do is they have to balance the SO2 and SO3 removal versus the cost of doing so. So typically you'll see a few different sizes of Trona. Unmilled Trona has a needle shape, a very seemingly well-defined crystal structure, but it has a coarser particle size distribution than milled Trona, and regardless of the porosity of a material, if the particles themselves are larger, the specific surface area, that's what SSA means, the specific surface area will be smaller. There's simply less surface for the same mass of material. So what that means is the operators will need to inject more of this larger Trona to hit the removal targets. Now instead, if you talk about reducing the particle size, that's beneficial because you increase the specific surface area. And you need to inject now less sorbent to hit the removal target. This has the, balancing effect of also adding cost to the operation. It still may be, on the whole, less expensive than using unmilled coarser Trona. But it does add cost because you're either buying the milled material, which whomever you're buying it from obviously has put time and effort and money into, so the cost of it should naturally go up, or you're doing some milling on site yourself, in which case the capital cost of the mill and any operational costs need to be factored in. There's an additional challenge in that finer powders typically have more difficult flow and handling characteristics. That is very well characterized. And so what you run the risk of, in essence, is if the Trona becomes too fine, if you mill it to too fine, you may actually have agglomerates. So there's kind of going to be a point at which you cannot mill it any finer than, or at least it cannot exist in the dry state as a smaller primary particle size. So we'll talk a little bit about the impact of size and surface area now. So before we go into particle size, I'll talk a little bit more about surface area. So when Trona is injected into the flue gas, it undergoes a process called calcination, which happens at certain temperatures. It's happening above, I think 90 degrees Fahrenheit, but it takes a little while. The customers we've talked to and the sources I've seen say that anything above 275 or 285 Fahrenheit, the calcination process typically happens very quickly. And essentially what happens is the Trona forms sodium carbonate, and it evolves water vapor and carbon dioxide. And the process, the evolution process, creates a micropore structure in the resulting sodium carbonate, and that means a higher surface area. Anytime you can take something that is non-porous or relatively non-porous and start creating pores, what you're actually doing is you're creating more reaction sites for the SO2 and SO3 to find and react with. And so here are some SEM images of what calcination does to the surface of the Trona. So the non-calcined Trona has a relatively non-porous structure. And then after it hits, I think this material was heated to about 100 degrees centigrade for maybe an hour. Now all of a sudden we have a micropore structure and the surface area increases. And that's beneficial because the more surface area you have, the less sorbent you need to inject, so the operational costs can stay lower. So here's some example data from the LA950. The LA950 is our laser diffraction particle size analyzer. And it's notable because it can measure both wet and dry. The data you're going to see over the next few slides was all captured dry simply because Trona has some solubility in water. And really for this application, because you're injecting it dry, you probably want to measure the particle size of the dry state as well. Typically what happens when you disperse materials in liquid is they disperse to a smaller state, a finer state than in air. And that wouldn't necessarily be indicative of how it's going to be seen, if you can think of it in that way, by the SO2 and SO3 in the flue gas. So in the LA950, these are 3 measurements in a row of a coarse unmilled trona. So this is a needle-shaped material. And here we see the LA950 powder jet accessory, that's the dry measurement accessory, delivering very consistent results across the D10, D50, and D90. And if you're not familiar with those terms, it's essentially the D10 is the point at which 10% of the particles by volume are finer than. The D50 is the point at which 50% of the particles are finer than, and the D90 is 90% of the particles are finer than. So it gives you an idea of the fine particles, the kind of middle particles, and then the coarse particles. What I'm also showing here is the LA950 assumes that everything is a hard sphere, so every material that goes into it, it's the easiest way to solve the scattering equations. So it assumes that it's a hard sphere, and because it assumes that, as long as we know the volume and the size, which we do because we get this result, we can calculate the specific surface area with the assumption that it's a hard sphere. So it's not a particularly accurate surface area because, again, we know that Trona before it's injected has a very low surface area because it's non-porous. And Trona after it's injected has a much higher surface area, but what is generally true, as we'll see in the next few slides, is that as the size reduces, the specific surface area increases. So why would you want to measure the size? You would want to measure the size because if you're buying the Trona from a supplier, and they say that the median size, the D50 size, should be less than, let's say 350 microns, you may want to screen the incoming material just to make sure that what you're getting is what you think you're getting. Likewise, as we'll see in this slide, where I've measured milled Trona, which is much finer in distribution. You may also want to measure it to screen incoming material if you're buying milled material, or you may want to use it in a classic particle size application to monitor milling endpoints. You could also monitor the milling efficiency and when the mill is starting to wear down as well. So if we were to overlay the coarse and the fine results, we'd see graphically there's quite a big difference. The fine result is much finer by more than an order of magnitude for the median. And the specific surface area as well is higher by more than an order of magnitude. And these measurements took, a single measurement with the powder jet took less than 1 minute to perform. That was actually a little bit closer to 45 seconds. So it's a very fast method, very fast confirmation of the expected particle size. So I'll talk briefly about the technologies themselves. So what we see on this slide are all the different technologies that HORIBA has, from laser diffraction for particle size to dynamic light scattering for size of much smaller materials, image analysis offerings for micronized and larger, and then the SA9600, which is our flowing gas surface area product. So this slide's more for your reference, just to see different different techniques that will all measure particle size and the different overlapping ranges. None of them are as fast a measurement as laser diffraction, which means that none of them tend to be as popular for quickly classifying materials. And how laser diffraction works, in a nutshell, is inside the instrument you have your material that's getting circulated through either some wet flow system, or if it has the powder jet accessory, which would sit on top, it's being injected through the measurement zone and then evacuated into a vacuum. And when you're passing material through the measurement zone here, we are using a red laser and a blue LED and a wet measurement only. And from those two light sources, we're generating scattering. So as the light hits the particles, depending on the size of the particles and certain other characteristics, we'll get scattering of different intensities at different angles. So we have a wide array of detectors from nearly 0 degrees to 166 degrees. And their only job is just to measure the angle, the intensity of the scattering. We know the angle. And so that's all this instrument is actually doing. That's all any laser diffraction instrument does, is collects that information. And then it moves it over to the computer, which has the algorithm, which will then convert that scattered light to a particle size distribution. Laser diffraction is very popular. It's the most common technique, really because it's extremely fast. It's a very easy technique to learn and to use well, which naturally means that the results then become much more repeatable. It covers a very wide size range. The LA950 can measure anything from 10 nanometers to 3 millimeters. And it can measure many different types of samples, from powders, suspensions, gels, emulsions, creams, so on and so forth. So the LA950 is notable because of all of the laser diffraction instruments on the market. This one has the lowest total cost of ownership. It will measure, it'll take a particle size measurement in less than 60 seconds, wet or dry. It can be easily set up for one-button operation, which makes it very useful for when you have to bring new operators online, or maybe you have multiple shifts who are going to be using it and you can't afford, or you don't have the luxury to send them all to our training course. Or maybe they're not all present when we do the initial training, when the analyzer is installed. So it's very nice to be able to just say, create a 4 or 5 bullet point instruction set to measure the Trona, and one of the instructions simply says locate the sequence file for Trona X or whatever it may be, and click the start button. Very nice. It is a very durable instrument. Even though this instrument is being used in many different R&D labs, it is robust enough where it can be used in a production environment. In fact, it's used by many mining companies to measure everything from gold to bauxite. It's the 9th generation HORIBA laser diffraction instrument. We've been doing this for a long time. It has a lot of many different refinements in it. And as I talked about, it has a very wide range. However, if you were looking for something slightly different from the LA950, we have the LA300, which is a much smaller design. So if the LA950 was several times the size of a computer monitor, the LA300 is about the same size as a laptop. That makes it very uniquely portable, and in fact it can be shipped from multiple locations just in something as simple as a Pelican case. In fact, that's how many of our LA300 customers choose to use it. It is also very durable, just like the 950. We engineer our products to kind of take a beating, because who knows, after we install it the first time, who knows where it's going to end up, and you don't make happy customers by having the service guy visit you 3 times in 6 months. The LA300, however, only can do wet measurements, no dry measurement capability, and it has a smaller range, so from 100 nanometers to 600 microns. Now this, for a milled Trona, isn't such a restriction. That's well within the range. For some of the larger Trona samples we've seen, the 600 microns tends to be on the, that would give us some pause depending on how large the Trona was. The SA9600 surface area analyzer is our flowing gas technique. It uses the BET theory to calculate total surface area. And it can measure from 0.1 to 2,000 meters squared per gram. Single or multi-point analysis, if you don't know what that means, single point analysis means it's essentially making one surface area measurement and then extrapolating the total surface area from that single point. Multi-point analysis just means you're taking multiple measurements, so your extrapolation has a little bit less error in it. But many times the single point is more than good enough for production environments, and it's much faster, one point as opposed to multiple points, as you could imagine. You could get it in a single station variety where it just has one measurement at a time possible, or a triple station variety. And in single point mode you can get up to 30 analyses per hour, which is very fast. And it's a very preferred option for quick and easy surface area analysis. So again, in a production environment where the material is not changing, this is the easiest way to measure surface area. And the reason we bring it up in this webinar, there's not too many customers we know of who are measuring surface area of Trona, but that's really what the interesting part is. So the higher surface area, the more reaction sites for the SO2 and SO3 sequestration, And monitoring particle size kind of indirectly gets you a surface area measurement. This will give you a direct one. Okay, so now I'll spend a few slides. Several of you had requested in the webinar registration some information about interpreting particle size results and also setting good size specifications. So I'll try and meet that need right now. So we'll start off just by making sure we're on the same page with regards to terminology. So when I talk about the LA950 measuring down to 10 nanometers, you should understand that that is several orders of magnitude different than the higher range at 3 millimeters. In fact, we go from 1, 2, 3, 4, 5, 6 decades of size. If someone were to talk to you about micrometers, that means the same thing as microns. In fact, most people will talk about it in terms of microns because it's a little bit less awkward to say than micrometers. However, we all say nanometers as well. It's a little quirk. So the basics of particle size. You have a particle, you want to measure the size, but what is the most meaningful size? Is it the width of the particle? Is it the length of the particle? Or is it even the diagonal? Is it some kind of hypotenuse of the particle? So a key takeaway, anytime you're doing a particle size measurement, regardless of the application, is that different size definitions will give you different results. And by extension, that means that different sizing technologies will also give you different results because each sizing technology tends to give you information about some different aspect of the particle. So what sizes can be measured? With the technologies we talked about today, excuse me, I got a little too ahead of myself. So with the laser diffraction technology we talked about today, it converts everything to an equivalent spherical diameter. So again, when I was talking about the specific surface area that is reported by that instrument, it has to assume that everything is a hard sphere, even for the size results, because that is the easiest way to make the math work to convert from scattering intensity to a particle size distribution. So even though your milled or unmilled Trona sample will have a size that, a shape that is much more similar to what we see on the slide on the left-hand side, the way the LA950 or any laser diffraction instrument will have to think about it as though it's a hard sphere. So that naturally brings a little bit of error into the process, but that's okay. We don't get worried about that error because it's built into every measurement. And really what you want to know much more often isn't the absolute accuracy of the size that's being reported, but it's the relative accuracy. So is it important that the D50 really is 18.2 microns, or is it important that the LA950 is saying that it is 19.2 microns, but that when you mill it a little bit longer, the whole size distribution shifts finer? Typically, that's what most people want. Is so long as the error is being built in for every single measurement, you can still get as actionable information as possible out of the instrument. I hope that makes sense. So when we talk about a particle, we're talking about a single particle. So when we talk about a particle distribution, it's actually many, many, many different types of particles, and they may have very different shapes, obviously very different sizes as well. And so when we talk about particle size, we're actually talking about just a single number for that particle based off of whatever metric we choose to measure. And a particle size distribution is the size, based off of that metric, for every particle we can measure delivered in a graphical format. So a particle size is a single number. A particle size distribution is many, many, many different numbers. And the reason we like particle size distributions instead of just particle sizes is because it gives us so much more information. Just looking at a single number can be completely misleading, and we'll see that in a few slides. So again, laser diffraction assumes a hard spherical model. So real quickly, we'll talk about different size metrics, different size statistics you can pull out of the size distribution that you may want to set your specification on. So if we're talking central values, typically that's the mode, median, and mean. And the mode is simply the most common particle size. So the top of the distribution, the peak of the distribution. The median is the 50% point at which 50% of the particles by volume are smaller and 50% of the particles are coarser. And then the mean you can think of as the center of gravity. It's the point where if you put your finger underneath the distribution, the whole distribution should balance. And what you should take away from this slide is that the mean is more sensitive to large particles, so that when you have a distribution with a coarse tail, the mean will always be larger than the median. And again, that'll become important in a few slides as I show an example where if all we looked at was the median, it would be a little misleading. So not a few slides, the next slide. So here we have a material. It's not Trona, but it is another mineral where there's two different materials, two different lots of the same material. And what we see here is data from the LA950. And for the first material, we're seeing a D50 of 472 nanometers. For the second lot, the D50 is 475 nanometers. Now that's not a big difference, 472 to 475. A 3 nanometer difference is within the instrument tolerance. But if we were to look at the mean, then all of a sudden we see a very big difference. So the mean size for the first one was 1.09 microns, and the mean size for the second lot is 1.29 microns. So now we're talking about, instead of a 3 nanometer difference on the median, a 200 nanometer difference on the mean. And that's entirely because of this small population of very large particles out here close to 80 microns or so. Now, we're not going to see 80 microns in either the mean or the median, but what we are going to see is the mean is going to be much more sensitive to the presence of these few large particles. So if a few large particles were important in your process, or if, say, you were monitoring the endpoint of a milling operation, you would probably be better served by monitoring the mean size as opposed to the median size. So I discussed the D10 and D50 and D90 earlier, and you should know too that it can be extended all the way out to the D100 and the D99. We typically don't like to recommend monitoring the D99 or the D95 simply because there are relatively few particles on the extreme edges of the distribution, and what that means is unless you have excellent dispersion and sampling of your material, you'll see a lot of variation. You'll see very poor precision on D95, D99, and especially D100, because there's so few particles that unless you get the exact same sampling and dispersion, what you may think of as a poor product being passed is actually a sampling or dispersion error. So we prefer to recommend nothing larger than the D90 simply because this is a much more stable metric, and it's much less sensitive to how the sample is prepared or how the operator introduces the sample. So if you see the D90 truly shift, you can put a lot more confidence in the fact that it's because the product itself is changing, or the process that creates the product. So here's something that's very common in milling operations, a bimodal distribution, where you might have your primary particle size, where you want to reduce the size to, and then some larger material. In fact, this is a very common dispersion case as well. So the challenge with bimodal distributions, or anything that has a more complex particle size distribution, is simply that if you choose a single number, or even three numbers like the D10, D50, and D90 to monitor the distribution, it's going to give you some misleading results. So inside the LA950 and the LA300, we have what we call a multimodal report. And what that function does is it essentially splits the distribution up as if it were being created by two separate size distributions. And what we're seeing here in the far left box is the D10, D50, D90, and mean values for the entire distribution, so not split. It was as if the entire bimodal distribution was being calculated. Excuse me. And the D50 comes in at about 25 microns, And this is curious because at 25 microns, which is roughly around this spot, you wouldn't think that that is any interesting point, right? If you're going to be monitoring the dispersion state of this material or the milling state of this material, you probably wouldn't want to choose a point that seemed to be in the middle of both modes. And the mean value at 30 microns is kind of in the same boat. So what happens when you start monitoring each distribution individually is now you can see that the D50 of the finer distribution is at 1.5 microns. This is kind of a meaningful point. And the D50 and the mean of the larger distribution is right around 50 microns. So again, 20, 30, 40, 50, again, a more meaningful point. And when this can be misleading is we've seen cases, not necessarily in the Trona industry, but just in general, we've seen cases where people who are supplying a material or a product which may exist in a bimodal state will send only one or two or three specs with it. So they might say the D50 has to be between 22 and 34 microns. And in this case, this material would pass. Now, is this really the material that you want, or do you really just want this primary dispersed, or maybe the primary mode with a small, manageable tail of coarse material? In a lot of cases, this is what the person on the buying end actually wants. It's just the singly dispersed material, which is why if you look at the D50 and the mean value for a bimodal material, it can oftentimes be misleading. One of the other things that's very, very good to do is if you're buying material or if you're screening incoming material, if you're classifying material to sell to someone, or if you're screening incoming material that you've bought, you'll want to make multiple measurements. If you just make one measurement, it can be misleading. You may have a sampling problem that you don't recognize, or a dispersion problem that you don't recognize. A lot of times powders that are shipped, if there is any kind of width to the size distribution, so multiple different sizes, what happens is many times you see the size of the powder, how should I say it to be more clear? So imagine you have a 1 kilogram jug in front of you that's filled with powder. If you shake it like it's been on a truck moving from point A to point B for a few days, a lot of times what you'll see is if all you do is sample from the top of that 1 kilogram jug, you're going to see a much coarser particle size distribution. And if you sample from the bottom of the jug, you'll see a much finer particle size distribution. Because what's happened is the finer particles, as you shake it up and down, the finer particles will percolate downwards. So they'll basically bounce in between the larger particles is the simplest way to think about it. And so you get a lot of segregation by size. So at the very least, you'll want to mix it up, and you'll want to take multiple measurements from at least different points in the jug or whatever container is being delivered into your lab. And what that'll do is it'll hedge your bets that you're not relying on a size result that came from maybe not the best sampling or maybe not the best dispersion. And the good news is, in the LA950, we have tools to make this kind of averaging process much simpler and easier to use. So the reason you would take multiple measurements is at the end of it you'd want to take an average value of those and calculate something called the coefficient of variation. And the coefficient of variation is important only because people who've been using laser diffraction to monitor particle size for years and years and years have all kind of gotten together and agreed that coefficient of variation is the best value to use to evaluate the precision of your results. So another way to think about it is the reliability of the results. And a lower COV value indicates a better precision and a more reliable set of results. But calculating the coefficient of variation is not trivial to do. It's not something most people will do with a pad of paper. Calculating the average of a data set's pretty simple. Calculating the standard deviation becomes more difficult with pad and paper. So the LA950 will do it for you automatically. Another nice feature in the LA950 is this graphical verification. So if you'd set up a particle size specification, when you make your measurement, you can build the specification into the measurement condition file so that when you do make the measurement, regardless of who's making the measurement, the operator can see very clearly whether or not this is a passing material on, let's say the D50, D10, and D90, or if it's failing any of the size metrics. And we're not limited to excuse me, we're not limited to monitoring only the D10, D50, and D90. We can do any number of different things. All right, so let's talk a little bit about citing good size specifications. One of the more common issues we run into with people who've set size specifications is if they're speccing on the percent under the curve, let's say, that can be very different than setting the spec based on size. So what we're seeing in this graph here is, let's say you have a material that is nominally 100 microns, has a median nominally of 100 microns. And you set up a size specification that says, okay, we'll accept anything that has a D50 with a 5% error, so anything from 95 to 105 microns. Because this distribution is so narrow, that's actually giving you a much larger error bar if we're looking at the percent of material that's passing, basically the percent of the material that's less than that median size. So in this case, a size error of plus or minus 5% is resulting in an undersize error of 20%. So they're not very similar. And what the takeaway for this slide should be is you need to understand not just that measuring particle size is important and that it's something you should do, but you need to understand, is it the size itself that's important? Is it the median itself, or is it the amount of fine materials I have, or is it the absence or presence of large materials? Because that'll help you decide if you need to set your specification by size or by percent finer than. And again, we're seeing a slide that talks about how we can set good size specifications. And in this case, the slide is saying that whatever you set as your external product spec or process specification, it always should be wider, and in this case, significantly wider than whatever your internal specification is. And this is one of those kind of common sense things. You don't necessarily want to give yourself headaches if you can avoid it, and so long as it doesn't adversely affect either your product performance or your ability to position the product that you want to sell in the market. The point here is simply, whenever you create a particle size spec, or any spec for any material, actually, any measurement, you want to include different error sources. And here we talk about lab error as some kind of aggregate error that rolls in operator error, sampling error, dispersion error, the actual instrument measurement tolerance error. In the case of Trona, as I talked about, converting a needle-shaped unmilled Trona material to a hard sphere has some built-in error. So when you set your internal specification, not the external specification, the internal specification should build in the lab error. And then when you set your external specification, it should always be wider in terms of size, both finer and coarser than. And so if we're building in the lab error to the internal specification, we need to examine the possible sources of this lab error. And as I talked about at the beginning of the presentation, we have several different pieces of content available right now on demand from our website that talks about how you can improve your sampling of powders or suspensions, how you can, it's not listed here, but how you can also improve the dispersion of the powders, either if you're measuring powders dispersed in liquids, or if you're using something like the LA950 powder jet to disperse powders directly and measure it in the dry state. You also want to do some kind of structured method development, and this is the type of thing that companies like HORIBA will help you with. It's in our best interest to make sure you have the best measurement method possible, because not only will that make you happiest because you won't have preventable headaches, but it'll also make us happy because, well, we like happy customers, and we also like, truthfully, we like running into you 10 years down the road when you want to buy the next analyzer, and not needing to match the error-filled data that unfortunately you might have been producing for the last 10 years. That's no fun for you, and it's definitely no fun for us. And the goal of all of these should always be, whenever you develop a new method, the primary goal is always reproducibility, right? If you can get the same results time and time again, then that will, number one, give you a lot more peace of mind that you're operating the instrument correctly, that it's a good application for your material, but it's also going to mean that you don't have to have the one particle size guru in the company running the instrument. You'll be able to pass the method along to however many operators you choose and feel comfortable knowing that they will get the same result you have. So that was the formal presentation I had for you today. We will get into the Q&A very shortly. I wanted to thank you for attending. And as I said in the beginning, we were a little light on actual Trona measurements simply because most of the people that are either mining the Trona and milling the Trona understand the value of using it for this particular sequestration application. It's more about how can you get a little bit better performance out of it, why is size important, why is surface area important, and then how do you set good size specs. So that's what we chose to focus on with the presentation today. If you have any other questions, you can always contact me. My email address is up on the slide here. You'll also get it in the thank you emails that'll be going to be sent out by GoToWebinar, thanking you for attending the event today. Treviranus isn't the easiest last name in the world to spell and remember, however, so if you do forget that and you want to ever ask us a question, you can always contact us at labinfo@horiba.com. Labinfo is a heck of a lot easier to spell and remember. And Labinfo has the added benefit of about 6 or 7 of us monitor that email address, so it's nearly impossible to ask a question to Labinfo and not get a response. And this email address is always available on our website as well at this quick request button. If you're not part of our newsletter, I would encourage you to sign up. That's how you can receive new software updates, new application notes, if we're unveiling a new accessory, or if all you want to do is attend the next webinar. That's always where we announce it. And that's what I had for you today. So I will pause and ask Jeff if any questions came up.